Welcome to our lectures on DC microgrid and control. Today we shall discuss about that modeling of the renewable energy. Mainly we take out first the wind energy, thereafter we shall do the modeling of the other renewable energy sources. So, today we are going to cover wind power generation system and wind turbine modeling, thereafter electrical generator modeling and the maximum power point tracking of this to track the maximum power from the wind energy. Now, wind power generations, it is we know all that wind power generation has gone with the last 3 decades and is considered one of the most promising renewable sources of energy, because of it is availability throughout the day and night, and harvesting is quite good. However, its integration to the power system has a number of technical challenges concerning security of supply in terms of the reliability, availability and the power quality. These are 3 challenges. Reliability, actually you may, if it is a thunderstorm or something, you have to have a pitch control and ultimately pitch control does not work sometime, those are the problem. That the availability of the wind to generate power at low wind speed is also a challenge, and also since it will be a variable speed, so you have to work with the power quality issues. Impact of the wind power system is mainly depend on its penetration level, that will come little later. How does it mean by that? Power system size, the mix of generation capacity, the degree of interconnections with the other system and the load variation. Since the penetration of the wind power generation is growing, so you can see that gradually that more amount of wind is contributing to our main supply. The system operator have an increasing interest in analyzing the impact of the wind power into the connected power system. That is something had become a mode of operation and study to how much wind penetration will have what kind of effect, because it is a variable speed, and how it will be changing and forecasting. Altogether a basic proposition has been come across. The grid connected connection system requires steady state and the dynamic analysis like voltage dip through capability. So, we require to understand it is actually when it is running at a steady state, what should be the generation, and if it is changing the wind speed, what should be its characteristics. Moreover, if load changes, and what should be its characteristics, because it may be a feeding to a local load instead of connecting to the grid. This leads to the detailed modeling of the wind turbine system in order to analyze dynamic phenomena in the power grid. So, that is something we require to see while modeling. All those details will be covered. Moreover, the wind turbine technology integrate power electronics and control, making it possible for wind power generation to participate in active and reactive flow of power or control. We have seen how you can change the flow of power, can control active and reactive power. Same control technique will be applied here with the help of the power electronics. Nowadays, most of the installed variable speed wind generators are based on the W-fed induction generator. So, where we will feed from the stator side as well as the rotor side, but new type of the wind generation based permanent magnet synchronous generators are also expected to gain the market popularity in the following years, but only problem in PMSG is that this permanent magnet available in a single country in a bulk, that is China. So, ultimately China controls the market, that is one of the biggest disadvantage of PMSG. So, let us talk about the DFIG first. W-fed induction generator configuration consists of a wound rotor induction generator, because you have to feed power in stator as well as rotors. In slip ring it is not possible. Induction generator with the stator winding directly connected to the grid. You can see that this is the stator winding. So, that will be directly connected to the grid, and the rotor winding connected to the voltage source back to back converter, which transfer the extracting power. This is the actually it can, if it is working in a super synchronous mode, then it will ensure, then it will extract power from the rotor also and it will supply. If it is working in a subsynchronous mode, then you have to inject power to the rotor to maintain its synchronous speed. The PMSG configuration needs or one of the advantage of that, this rotor power sees actually only the percentage of the bulk power. For this rating of this dual converter is quite low compared to the total rating of the permanent magnet, compared to the total rating of DFIG. The PMSG configuration needs a full power converter and allows the use of multipolar generators, making it possible to suppress the gearbox. So, this is something, this is the something we may not have a gearbox here, and here we can use a permanent magnet synchronous motor or generator. In this case it will be generator, thereafter you may have a back to back AC to DC, thereafter DC to AC converter, and thus you can have an electric transformation and you do not require any gearboxes to make this actually the pole adjustment, and ultimately you will feed the power. But disadvantage is that this converter will see the whole rating of the PMSG, but generally it is basically deals with the slip power. So, this power is quite low in case of the DFIG. So, power electronics ratings of this back to back inverter and converter is quite low compared to this PMSG, but here you have a gearbox, you do not require any gearbox. Wind turbine electrical generation system power comes from the kinetic energy of the wind, and it can be expressed as a kinetic power available in the stream of the air multiplied by a Cp factor called the power coefficient. Cp mainly depend on the relations between the average speed of the air across the area covered by the wind wheel and its angular speed of the angular speed and the geometric characteristics of the turbine, including the instantaneous blade pitch angle. Professor Soumitra Banerjee has done an NPTEL courses quite long ago on renewable energy sources. You are requested to refer all those details there. So, the power extracted of the wind turbine has the following expressions, that is Cp into wind, and if you can expand, that is the coefficient of the power, that is half, rho is the density area, and it will be the proportional to the velocity cube. So, while increasing, if velocity of the wind speed is doubled, then energy transfer will be actually 8 times. So, it is quite huge in terms of the power generation with the smallest change in the wind speed, and therefore, the different approach to model the power coefficient. The common approach is to use the analytic expressions form, that is Cp, lambda and theta. It will be C1, C2 lambda I minus C2 theta 3 and so on, while lambda is the speed ratio and is identified by lambda equal to omega t r by wind speed and lambda I equal to 1 by lambda plus C8 theta minus C9 theta, where we can find out C1 to C9 can have these values, 0.5, 0.16, 0.4 and so on are the characteristics constants of the wind speed, and where theta is the blade pitch angle. Knowing the wind speed and the angular speed of the wind turbine and the blade pitch angle, the mechanical torque of the turbine shaft may be computed. That is very important thing, that is Cp V wind omega t, that will be basically the function of these two parameters half rho a v square, where T prime T is the wind turbine torque. So, let us understand the power characteristics of the wind turbine. The power characteristics of the twin turbines are defined by the power curve. We shall just come to this power curve, which relates the mechanical power of the turbine with the wind speed. A typical power curve characteristics by the wind speed: cut in wind speed, rated wind speed and cut out wind speed, and it will be illustrated in the next figure, that is figure 3, where Pm is the mechanical power generated by the turbine and the Vw is the wind speed. So, this is something that you will have to see. So, this is the cut in speed, below that it is not possible to generate any energy, and this is the theoretical pure curve, and actually this is the generator control, and in this region you require to operate. Thereafter, stall or the pitch control, you have to align in such a way that maximum air should pass and it will not be affected by it. So, here you will start, this is the rated speed, and there actually you will not allow the wind speed to go beyond it, and thus you will have a pitch control, and above this wind speed you will have a cutout. The cut in wind speed is the speed at which turbines start operating to deliver power. It is a lower cutoff. The rated wind speed is the speed at which the system produces nominal power, which is also the rated output power of the generator. Say it is a 10 meter per second square. So, you take that value of the wind speed as a standard, and maybe 4 meter per wind speed is a cutoff. So, in that region we say that this is the theoretical power curve. The cutout wind speed is the highest wind speed at which turbine is allowed to operate before it is shut down. If it goes above it, we require to shut down for the for the wind speed anomaly. It is due to the thunders or hurricane or whatever may be. If you try to operate that thing, we may actually damage the blade. Now, the generator of the doubly fed wind turbine is wound rotor asynchronous machine. Assume the rotor and the stator winding to be placed sinusoidal and the symmetrical, and the magnetic saturation affects the capacitance of the winding is neglected. Now, taking the positive, the current flowing towards the machine, the relation between the voltage and the machine winding and the current and its derivative can be rewritten as Vs V supply of voltage that equal to I into S, that is the flux linkage into the system, that is actually it is n into phi, that is let us say lambda. So, that is in the stationary frame, that is for the stator, same thing it will be on the rotor, and where this is the stator parameter, stator voltage of the ABC phase, and this is the stator current of the ABC phase, where the stator voltage and the current and the are the rotor parameter respectively, and lambda ABS, lambda S ABC and lambda R ABC are the rotor flux linkage and stator flux linkage and the rotor flux linkage respectively in ABC frame. Now, where there can be a cross link, the stator and the rotor flux linkage ABC vector are defined by LSS, that is for the mutual inductance, into IS ABC. Then this is basically the mutual, it is S and R. Same way this will be the symmetrical matrices you will find, it will be RS, and this will be for the rotor. Generally what happen, if you write and expand LSS, then you will find that LS into MS, they are to half MS and half MS. Again this will be LS plus LMS, and this is the terms of this diagonal element, and this will be the terms of half LMS, the off diagonal element, that is between the mutual inductance between the stator and the rotor. Same way you will find that the diagonal element is LR, LR plus MLR and so on, and the off diagonal element will be half LMR. I request actually a student to go through any machine analysis book of Cross or other to understand this phenomena. Now, LSR ABC equal to LRS ABCT. So, we can split it, that is the theta is the angle between stator and the rotor with any predefined reference, and then we will find it out the total angle. So, we will actually convert this transformation, that is basically ABC to LR, that coefficients are cos theta, sin theta and so on. So, the mechanical torque can be written as a function of the machine current as, so that is the number of pole IS and IR of ABC, and these two element will be 0, that is SR ABC and RS NBC into the current of stator and rotor, where similarly this NR ABC can be written as LSR into sin theta and the sin theta R, and there will be a different phase shift to accommodate the 180 degree phase shift of this balanced 3 phase system. Now, as this equation have a hard dependency on the rotor angle position, please see that actually theta R has been written. So, for this reason, so it has a hard dependency on the rotor angle position. The Park transformations used to transform the variable to integrate the dynamic equation of the machine. Ultimately, we shall go back to the your ABC to the DQ, and thus this is actually VSQ and VSD. This is basically the DQ of stator side, and VRQ and VRD are the rotor side, and you can find that the expression will be surviving is that this is actually LS into ISQ. Thereafter IST term here it will be 0 because there will be no component of the resistance here, but there will be a mutual component, that is actually here there is M into RQ, and thereafter RD will be 0. Similarly, we can split that thing and ultimately you can generate this vectors, and ultimately you will have a cross reference in these sectors, that is RS into SQ. Thereafter this will be the cross term LS into omega S into SD you have seen while controlling this other parameter, and with VQ there won't be any real component, RQ will be 0, and again with the omega s m will come, that value will be the RT. Similarly, it follows for the other, and you can write it by the inspections. So, and also this is a 0 sequence component if it is there. So, that will be actually Ls into stator, and it will be in a 0 sequence. So, it is, you will have this stator as well as the rotor. Now, we understand that the value of Ls is 2/3 LMS plus Ls, and thus, and also Lr, it actually 3/2 Mr plus Lr are the stator and the rotor winding of the self inductance coefficient, and thus Am is basically become 3/2 Lsr, and is the coupling coefficient between the stator and the rotor winding, and S is the slip defined as the relationship between the mechanical speed and the reference frame of reference, where S equal to synchronous speed minus actual speed by synchronous speed. Please go back, for this reason you will find this S term actually associated with the rotor. So, in the stator there is no S term, and please do not confuse. Sometime we have seen that people confuses that S as a Laplace. No, it is not Laplace. We are writing totally in a differential form. So, it is not in a Laplace domain, it is in a T domain. The torque expressions of the stator and the reactive power, which are the control objective of the rotor side converter control, and it can be rewritten as Tm in terms of this actual in terms of the reactive in terms of the torque in dq frame, that is 3/2 P into m ISQ/RD minus IST/RQ, where P is the number of pole pair, and similarly the reactive power, that is 3/2 VSQ into ISD minus VST ISQ. So, this is the modeling, and you require to spend time on little bit on the machine design part. Essentially, it is the basic motor. Now, let us come to the picture. The control of the variable speed wind turbine below the rated speed is achieved by controlling the generator. So, you have a generator side control. What we do generally? So, these are the different maximum power point taking. We try to actually align this pitch so that it actually get the maximum power. The main goal is to maximize the wind power capture at different wind speed, which can be achieved by adjusting the turbine speed in such a way that the optimal T speed, the ratio is maintained. So, that is something you require to ensure, and that is the control. Figure 4 shows the typical characteristics of the wind turbine operating at different wind speed, where Pm and the omega m are the mechanical power and speed of the turbine respectively. Now, for a given speed, each power curve has a maximum power point, you can refer. So, particular wind speed. So, this point, this point, this point, and this is the wind speed. It is 0.5 per unit, 0.6 per unit, 0.7 per unit, 0.8 per unit, 0.9 per unit, and something like this. And the trajectory of the MPPS, that is maximum power point, represents the power curve, which can be described by the figure has been shown in figure 4, and that is Pm is proportional to omega q. The mechanical power captured by the turbine can also be expressed in terms of the Tm, that is mechanical torque, and the turbine speed. So, of course, we can equate this to, and thus Tm we can see that it is proportional to omega square. Ultimately torque will be proportional to the wind speed square of the wind speed. So, considering those aspects into the mind, we have to design it, and this is the figure of the maximum power point control with the wind turbine profile, and this is the wind turbine. There is a gearbox, you are feeding rotor and the stator DFIG, and this is the back to back AC to DC, DC to AC converter, and stator directly connected to the grid, and you have a digital control that will actually integrate power or actually take away the power from the system. The relationship between the mechanical power, speed and the torque and the wind turbine can be used to determine the optimal speed and the torque reference to the control of the generator and to track or to operate at the maximum power point. The power curve defines the maximum power that can be produced by the turbine at different wind speed. The wind speed is measured in a real time by the wind speed sensor. The power reference Pm is generated and sent to the generator control system, which compares the power reference with the measured power Pm from the generator to produce the control signals for the power converter. This is the overall picture of the power converter. Through the control of the power converter and the generator, the mechanical power Pm of the generator will be equal to the reference in steady state at which the maximum power operation is achieved. This is quite clear. Now, we have to say about something on the MPPT with the optimal tip speed ratio. This method is the maximum power operation of the wind turbine is achieved by keeping the tip speed ratio to its optimal value. The principle of the control scheme is shown in the figure 6, where the measured wind speed Vw is used to produce the generator speed reference according to the optimal T speed ratio of lambda. The generator wind speed Vm is controlled by the power converter and will be equal to the reference in steady state at which the MPPT is achieved. Now, you see that MPPT with the optimal torque control. This is the wind sensor, and ultimately that from there we will calculate the value of the wind speed, and that value will be put it, and from there actually lambda OPT by RT, from there reference omega will be controlled, and by digitally controlling, by taking power and adjusting, injecting power, you will ensure that this rotor rotate at that omega, and thus it will track the maximum power. So, this is called optimal TSR control of the wind turbine. The maximum power operation can also be achieved with the optimal torque control according to the equation 16, where the turbine mechanical torque Tm is a quadratic function of the turbine speed. You have seen it in this equation. And the figure 7, what does it do? So, it sends the speed from it square it out from here, and thus you have a reference torque, and you will control the torque of the system. This is called optimal TSR control of the wind speed. And figure 7 shows the principle of the MPPT scheme with optimal torque control, where the generated speed omega m is measured used to compare with the desired torque reference Tm. So, in that way you will have both the control, you have a reference omega m and try to m, and here is a torque control. So, both are being used, that is called optimal torque control method for tracking MPPT. So, what we can conclude from here is that the coefficient for the optimal torque can be calculated according to the rated parameter of the generator. Through the feedback control, the generator torque Tm will be equal to the reference torque Tm prime Tm star in the steady state, and the MPPT is realized. It is noted that there is no need to use the wind speed sensor in this scheme. So, in this scheme you do not require any wind speed sensor, here you require the wind speed sensor. So, for this reason TRS method of control is been preferred. Thank you for your attention. We shall continue to our designing and modeling of the different kind of converter in our next classes.